What's up, guys? Welcome back to channel. And today we are going to talk about inverters and how we can design a simple inverter based on a microcontroller. So this is one video part of the series, and the series may contain 3 videos or maybe 4. And in this video, we are going to talk about the basic components of the inverter and circuit, how we can analyze the circuit diagram of a microcontroller based inverter. So first up, we have the microcontroller. So this is an Arduino, and we can use it to generate the waveform that we need uh, to get the output from the transformer. So this basically is the brain of the inverter, and it will be controlling all of the electronics. And if we uh, remove the Arduino, we have to do all of its coding that we do inside the chip with different chips, and it's gonna be too complicated to understand. So for the ease of programming and ease of designing, I'm going to use the Arduino. So to convert the DC voltage to alternating current AC voltages, we will need to use a transformer. So when choosing a transformer, we have two options. One is the ferrite core transformer that is used in most of the power supplies, and the iron core transformer. So by the way, uh, these transformer, even though they are small, they have a high current capacity, which means they can this even a tiny transformer of this ferrite core type can output a high amount of current than this uh, size iron core transformer. So this is used in a 430 watt power supply. So it can convert 430 watts, and this is used in inverter, and this is about 1 kilowatt maybe, but you can compare these two. With two of these, we can turn on the same computer, but uh, with iron core it's much bigger. So but uh, to drive this, we need a high frequency, but for driving these we will need only 50 to 60 hertz, which means the current will oscillate 50 to 60 times per second. So this for driving this transformer we will need around 20 to 80 maybe kilohertz. There's quite a big range, but this has only 50 to 60 hertz range, but this has a wide range of operating frequency. And uh, um, since we are using the Arduino, this can't operate at that much high of a frequency. So we are going to use the iron core transformer. By the way, also, if we are going to use the uh, right core transformer, we would have to convert the high frequency signal into low frequency signals, because our house electronics uses 50 to 60 hertz. By using an iron core transformer, we can skip that part and directly connect the output to our appliances. So these transformers are reliable while these are more efficient. So I'm going to use the iron core since it will make things easier. So now we have picked up our transformer and the main electronics. Also, these are part of the main electronics, uh, the MOSFETs. These are the drivers for the transformer. Arduino can't switch the transformer directly because it has a low current capability, and we will need to use MOSFET driven by the Arduino driving the transformer. So the signal will be received by the MOSFETs, and the MOSFETs will connect the supply voltage to the transformer according to the waveform. So and we will need also need some additional electronics like the optocouplers to isolate the signals and for feedback. Uh, and that's uh, almost it. So let's take a look at this circuit diagram. Uh, so this uses two PNP transistors to drive the MOSFETs. This design can be optimized to use through four transistors, two NPNs and two PNPs. Um, Maybe I can change that in the future because this is a open source design. Everyone can change their uh, change the diagram according to their own interests. So um, let's analyze this. And first of the ground is connected to the source of the MOSFETs. So the third pin of the MOSFETs is connected to ground. And when initially we connect the circuit to the battery, the ground voltage comes through here, goes to the base. By the way, these are PNP transistors. So if their base is connected to the ground, uh, they will be turned on. And so lights gone. So in this case, the transistors are initially on, and the voltage goes through here to the base, and the collector and emitters will allow current to flow in this direction, which is also connected to ground. And the uh, transistor will be on, and the gate will be pulled to ground, which is this pin. The first pin is the gate, uh, and it will be pulled to ground. So when a MOSFET is pulled to ground, the N-channel MOSFETs, they are um, not not closed; they are open. So this 1K resistor is less than this emitter to collector resistance. So this 1K resistance is higher than the emitter collector resistance. So the current will flow from here to the gate, and the gate is grounded. So nothing turns on yet. So when we output the signal, get the output from the digital pins of the Arduino through the 1K resistance. So the 1K resistor is lower than this 10K resistor. So the signal can override this the ground connection, and the signal can be driven to the base. And this transistor will be turned on and off according to the AC signal, and it will connect the gate through this 1K resistor to the supply voltage. So that's how it works. So there is an additional component right here, which is the linear regulator, which is used to power the Arduino. um, I'm using the 7805 IC for that. You can use switch mode regulator if you want. um, so there was an error in the circuit diagram. So I fixed this. Here's what I did. There was a resistor between the drain and source. Um, uh, so this resistor was meant to discharge the internal capacitor, but the internal capacitor is between the gate and source pin. It's right here. You can see two plates. Um, so misplaced the resistor. So I you have to connect the 10K resistor between the gate and source pin, and when there is no power to the gate pin, the gate capacitor will be discharged through this 10K resistor. The 10K resistor will be sufficient enough to discharge the capacitor fast enough to run this circuit reliably. So uh, right here in the corner, there is the feedback circuit. Um, there is 4 wires at the AC output of this transformer. So uh, there are different voltages. One is you can get the 230 volts between the black wire and the green wire, and other voltages between the other wires. So uh, I would have to take a low voltage than 230 volts and convert it to 0 to 5 volts. So uh, first I will need to rectify the voltage into DC and then filter it. And after that, I will have to divide the voltage into uh, uh, 5 to 0 volts. So um, the AC voltage comes from the secondary, and it goes to the bridge rectifier and filters by the capacitor and divided through the resistor. By the way, the output is taken from here, not from here. So the output is the AC signal, and uh, uh, the rectified voltage is the feedback voltage that is used to sustain the 230 volts output. So it's a very simple design. You can add a display if you want, and battery indicators, alarms, and stuff. Um, also, the advantage of using a microcontroller is you can upgrade the inverter through software, and without having to open it and desolder something or anything. Uh, for example, if you need to add protection, overload protection to the circuit, you can just read the duty cycle of the change waveform. Like if the duty cycle is over 80%, the the alarm should go off in the circuit. So like that, you can add the improvements to the circuit easily. So that's it for this video. In the next video, I'm going to build the circuit on uh, Vero board or dot board, whatever you call it, and test the circuit. And we are going to keep improving the circuit. In the future, this design may be changed. So stay tuned. Until then, bye bye.